Okay, now that we've had a day or two under our belt about logarithms and introduction to them, we're now going to start simplifying and evaluate the expressions and some equations that involve logarithms. How do you actually manage subtracting, multiplying, anything like that with a logarithm in the equation? So to do that, we will present some properties. So look carefully in these. We have all our properties of powers on the left-hand side, which you should be familiar with. Most of them are dealing with a base and then some exponent. So the first one, b to the 0 equals 1. We know that when you take any number to the 0 power, it equals 1. Second one, when you have any number to a power, it has to equal that same number to the same power. It was sort of like that one-to-one property we were talking about. So if you know the bases are alike, then the exponents have to be equal. The third one down is our power of a product. Power of a power, sorry. B to the m is a power, and n is a power. So we learned that you would multiply those two because we would have n combinations of b to the n, which is b to the m times n. Versus the other one people get it confused with is, what if I have two numbers with exponents? So the difference between the third one and the fourth one here, if I have two numbers with like bases that I'm multiplying, you go ahead and you add the exponents. And last but not least is if you're dividing, it undoes it just like the addition would. You would subtract those exponents. So shortcuts, and we've worked with those in Algebra 1, a little in geometry, and a little already this year in Algebra 2. So what do those same properties look like in logarithmic form? That's what we have to get used to. Because remember, of or pertaining to the exponent, so we have to rewrite these, and there's going to be logs in them. So let's take them one at a time. If I took the zero product property rule, took it through our magic, the zero product property rule would turn into the log of 1 in base b equals 0. If you don't say log, you could say the exponent for the number 1 in base b is equal to 0. The exponent, when it's 0, is always equal to a 1. That's what we said earlier. So that's what your b to the 0 power equals 1 looks like in log form. So b to the n equals b to the n. This is one I refer to a lot of times as duh, because it seems so simple. If we have the log of b to the n in base b, now remember that doesn't have to be a 10, equals that exponent. So I'm going to read it with those words. The exponent for the number b to the n, which is in exponent form, in base b is its exponent. So I like to call that duh because what's the exponent on the number b to the n if I'm in base b? N. So it's sitting right there for you to grab. The answer is visible. All right, let's do the power of a power property. B to the m taken to the n power. B to the m times m. I think we have room right there. So look what it turns into. And remember, both sides of these are shortcuts, and that's why we're learning these, because we're going to be able to use equations now with these logs in them, and we want to be able to shorten them, make them easier, answer, and solve a problem that might have these properties involved in them. So if we said the log of our number x to the n in base b is equal to n times the log of x in base b. So notice on this one that what was the exponent here comes down and becomes the multiplier here. So if you ever have the log of a number in a power form and it doesn't equal itself, the power, like on the previous one, then you know that that exponent has to be a multiplier, has to come down and be a multiplier at the same level as everything else in that problem. So that's the key there. All right, with that, just get rid of. Now let's do our like bases, add the exponent rule. Whoa, sorry, John Green craziness. if we bring b, let's just put it down here, because I think we'll have to bring the other one down there too. The log of our product, xy, in base b. So what we see is when we had multiplying and add the exponents in log form, here's where the multiplication is. And we can see that that multiplication turns into, notice, two separate addition problems with each of those values in their own log. So the log of a product in base b equals the log of each part of that product separately, added together. All right, last one. What if we do the division? The division of a number, so you can see here's the division of a single number in log form, will always turn into the log of the numerator minus the log of the denominator. So you are seeing in division we still get subtraction like we talked in the rule, and here in multiplication we get addition, add the exponents, but it's a little different look. You have like logs, etc. So we should now be able to use those properties in some equations. The only other one that I want to hit on, it's not a logarithmic property as the other 5 just were. This one is exponential, logarithmic, inverse property. So if you look at this, look at the left-hand side. The log of b to the x in base b is equal to the x. Because for most of you, you're saying, if we're rewriting this one, b is my number, x is the exponent, and it's supposed to equal that number, b to the x. And it does. So my number came here, my exponent came here, and b to the x was the number we were actually evaluating. Same way we've always been writing it. Inverse means, so now we have the log up as our exponent. Look at this. This is the log form, really, because it leads off log equals. This is our exponential form, but that exponential form has a log up in the exponent. So let's take this and say, well, wait a minute. If we follow the rule that says take exponential to log form, we should be able to. So it would start out the log of the number I'm assessing, which was x, in base b has to equal the number that I'm evaluating, which has to be that I'm evaluating it as its exponent. So the log of x base b. So let me again show you with arrows where the things came from. So if I took log form and turned it to exponential, which is what I just did here, and now I'm taking exponential and turning it into log form here, watch where my values went to. Same positions we've been using all along. So in log, you always start with log, so I started with log. I then place the number I'm evaluating using the base I'm evaluating has to equal my exponent, which is here. And if you look at those, they are identical. The log of x in base b equals the log of x in base b, just like on the left, b to the x equals x. So you either can rewrite them or you can use the exponential log inverse property and just recognize that's what it would be. That one's a little tougher, but we'll work through it. So let's try a couple. So let's start with log of 7 to the power of 26.8 in base 7. So notice we're not in base 10 anymore. It's some of your comfort zones. But let's work through. What form is this? Log form. We need to maybe rewrite it in exponential if that's not making any sense to you. But let's go back and analyze that. If you don't say the word log and you read it for meaning, you would be saying the exponent on the number 7 to the power of 26.8 in base 7 is what? And I think your brain is going to say something. If it doesn't, then your only choice is rewrite it in exponential form, which means 7 to the power of, that's the missing piece, has to equal our number that's being evaluated. So now when you step back and look at that, you have to say our answer is 26.8. Next one. Log of m to the n in base m. Again, it's in log form, but if you don't recognize what your solution is when you read it, then you probably will want to write it in exponential form. So here we go. Let's read it for meaning. The exponent on the number m to the n in base m is what? Well, the exponent's pretty obvious. It's n. Now, if that didn't make sense to you, then you're going to write it in exponential form. What is my base? M. What is my power? We don't know. That's the missing piece. What does it equal? The number we're assessing is m to the n. You then look at those two things and say, well, wait a minute. That thing I'm missing has to be equal if I have the same bases. So the missing piece had to be n. That was one of our properties. Next one. What's the log of the number 1 if I'm in base pi? Now there you go. You don't even have a number. You have a symbol that represents a number. You still do it the same way. So again, read it for meaning. What's the exponent on the number 1 if I'm in base pi? If that doesn't make sense to your brain, then rewrite it in exponential form. Right? Here we go, because this is definitely log form. So what's my base? Well, pi is. What's my exponent? That's the part they left out, so question mark. Has to equal the number we're assessing. So what power of pi has to equal the number 1? You should know any number to the 0 power is equal to 1. So what's the log? The log of 1 in base pi is actually equal to 0. And that's how you write your final answer. Next one. What's the log of 1 in base m? Same thing. What's the exponent for my number 1 if I'm in base m? And you know, it's just like the last one, 0. If you need exponential form, you're saying, what's my base? M. To the exponent, we don't know, has to equal 1. How do I get a 1 using exponents? M to the 0 power. So the unknown would have to be our 0. Now, here's one with our subtraction in it. And you got to remember and go back to our properties. If I have subtraction in 2 logs, that means, oh, we can rewrite it as division in 1 log. So what that means is I should be able to say the log of 1 in order, 3 over 48 in base 4. So you're saying, am I done? Not quite, because 3 over 48 is a fraction that's not in lowest terms. 3/48 reduces to 1/16. So now am I done? Look at it again. You still have a single log form statement. That log form should be analyzed. What is the exponent on the number 1/16 if I'm in base 4? Most of you should be able to say -2. If you can't, then your next step at this point would be to write me exponentially. That's log form, so go to exponential form. And your brain can think of it, or you can write it, and you'd be thinking, what's my base? 4. With an exponent, we don't know. That was the missing piece. Has to equal 1/16. So then you either know it because your multiplication tables, or you start thinking 1/16 is what in base 4? And so you think, well, 4 times 4 is 16, so that's squared, but it's 1/16. So you start doing something like this in your brain because of your common factors and multipliers. So you should be able to tell me that that's a -4. Or -2, sorry. This one is split up. It's a little bigger, 3 parts. So you do it in order. You follow order of operations just like we always have. So right away you're going to say, I can only do 2 things at once. I'm going to do those 2. That looks a lot like the last problem. So I would turn this into the log of 85 divided by 17, because the subtraction turns into division as a single log. Then I would still have the plus 1/2 times the log of 25, which we didn't touch. Okay, so the log of 85 divided by 17, most of you done the numbers there. That's the log of 5. Now there's nothing more to evaluate here until we finish the right-hand side. So start looking at that. Yes, there's an addition, and you know addition has some multiplication relationships, but that statement that's left over here has that multiplier out front. And what did we say about that multiplier out front? One of our properties says I should turn into an exponent. So if we rewrote this, another way to write this same statement would be this. But your brain should be saying, wait a minute, 25 to the 1/2 is nothing more than saying the square root of 25. So then we're looking at another way to say log of 5. So if that's the log of 5, and the first part already came out to be the log of 5, what's left? The addition. You cannot just say the log of 5 and the log of 5 is 10, because there's a product that says if I'm multiplying like and I add, then I should be multiplying those and writing them as a single log. So you should write 1 log, and 5 times 5 would give us 25. Now, if they wanted an actual number, you would go to your calculator on that one because it's not a perfect power of 10. But in this case, I think they're going to have a direction maybe like write as a single log. It said simplify. It didn't say evaluate, like tell me the number. So simplify. We got it down to as simple as possible. So log of 25 would be our final answer. Next one. Let's see what they throw at us. Looks similar to the one we just did, but it had a triple. Now we only have 2. So that should make it even easier. If I have 2 logs, the simplifying is to write it as 1. They're the same base, that's you're noticing. So in adding, that means I should be timesing. So 45 times 5, do the math, 225. So the log of 225 in base 15. So now ask yourself, what's the exponent on the number 225 if I'm in base 15? And if you know your times tables, you should be able to say 2. If you don't know your times tables that well, then you're saying 15 to what power equals 225 as your thinking step. And then you should come up with the 2, even with the help of your calculator. All right, what else do we have? Oh, okay, we got some radicals and some multiplying. So I would think of this in a couple ways. You've got your multiplier out there. So this 2, you got to be thinking that's that multiplier out front. So let's rewrite this as a single log with our base, and that 6 root 6 is our value. But if we bring that 2 out as the power, which is what the property says, now we've got this statement. So let's calculate what that number would actually be. Everything inside must get squared, so we'd have 36 for the 6 times 6, and then root 6 times root 6 would just give you the whole number 6. So 6 times 6 is 36, carry the 3, 216 is what it looks like. So after we simplify, we've got the log of 216, all on the same level, in base 6. That's not a division sign. I should have probably not written it, just thought of it. So what is the exponent for the number 216 if I'm in base 6? So that means you need to know your powers of 6. And if you do, you're going to be saying 3. If you don't, then your thinking is exponential form. 6 to the what power equals 216. And then you pick up your calculator and you work the math. Okay? So all the properties will be used. Now, because we'll be spending a couple days with this new stuff, if you want to stop the video at this point, you can. I do have a couple more examples that'll be from part 2. So you can either continue watching now or just pick it up later from this point on. Okay, so if you're continuing, we're talking about now, let's switch it, and the difference is going to be we have equations, not just expressions that we have to simplify. So when they say solve again, we know solve means find the variable. So there's really nothing to do when you start looking at just the left-hand side here. Okay? If we have just the log of x, there's nothing. So start thinking, I got to be looking at the right-hand side. And I see a couple things. What jumps out based on our properties? Well, number one, you should be looking at that 4, the multiplier out front. It's only out front of the log of 2. Also, this addition sign is your next hint as to what properties we're using. So don't do everything at once. Let's do it in pieces. And that 4 would turn into a single log, same number, same base. What base are we in, by the way? 10. Good. And that number would have to be taken to that power. And then we still have plus the log of 3. So if we finished here, the log of 2 to the 4th. The log of 2 to the 4th, doing the math, is a 16, plus the log of 3. You can't just add logs like regular numbers. You have to be thinking log in addition would turn into a single log as a multiplier. So 16 times 3, log of 48. If we did not have, and I've been a little lazy here doing this as we went, we've got the log of x coming down. We got this down to a single log. That's exactly what this was. So now we can look at this and say, wait a minute, x has to be 48. The missing piece is solved. Okay, you don't have to do any more math than that. It's all about the properties. So again, look at the left-hand side. We want to get down to a single log. So what can we look at? The 1/2 is key here, and this time it's a subtraction sign. So go for it. I'm actually going to leave this one for you to rewrite since it's so similar to the other one. Keep working until you get down, however many steps it takes, to get down to the log of y. And if you get down to a single log over here, then you should be able to compare and say y equals. But try it, and we can talk about that one as part of our work when we come back together in class. Now, these ones say evaluate. So look carefully. A little different. There's no equal sign, so we need an answer. The log of 27 to the 8th power in base 3. Log in base 3. Now, it'd be really great if that number that's there was in base 3, because it would make it so much simpler, but it's base 27. But wait a minute. Oh, 27. Oh, yeah. Do you know your times tables? So really, we could rename that 27 as 3 to the 3rd. I'm not changing anything else in this problem. So now, thinking about it, how many 3's do I really have? Because that is a power of a power. So I'm not changing the log. I'm not changing my base. What is 3 to the 3rd taken to the 8th? And you should be saying, yes, that's 3 to the 24th. So now, apply your power rule. What's the exponent on the number 3 to the 24th if I'm in base 3? And your answer definitely should be 24. Sitting there, grab it, done. So the key there was getting your bases on your regular number and your base in your problem to be equivalent. Then it was easier to compare. You could have taken it all the way out to 27 to the 8th, but that would have been a huge number. All right, let's try the same thing here. We have some more properties. This one reads, we've got addition, which is key, but we've got a mess here and a mess on the right-hand side. So each piece needs to be simplified as far as we can first before we do any addition. So ready? What's the log, or in this phrase now that we're getting used to this, what's the exponent on the number 7 to the 4th if I'm in base 7? And brain is saying 4, not the log of 4, 4. So that came out to a nice whole number. right, on this one. What is the exponent for, this is in exponent form. This is not in log form. So if your brain needs to rewrite that, let's do that. It's in exponent form. Let's write it in log form. So I'd have, this is my workspace over here. So I'd have the log of my number that's being evaluated, which we don't know. So the log of x in base 5 equals my exponent. And that was one of our rules. Look at that. So you can look. Everything is the same. The logs are in the same spot. The 5's in the same spot. So what's that leave? The x and the 3 have to be equal. So we have come down to nothing more than 4 plus 3, which is 7. So once you simplify each part, then we're good. So here's another one of those. You should have represented this, just like in the last one, as that inverse exponential logarithmic form. So you should know that if you have a number 9 to the log of 2 in that same base, that the answer just came out to what that exponent was. So we should now be able to say, hey, that's 2. Minus, now be careful, what's the log of the number 1/4 if I'm in base 4? In English, or for meaning, it means what is the exponent on the number 1/4 if I'm in base 4? Most people can say, hey, that's the number -1. And now look at what we have. We don't have to do any log division. We just have to do regular subtraction, and we end up with an answer of 3. So you now have expressions that need to be simplified, equations that need to be simplified. We're using all of those properties we discussed early on, the 5 exponential to logarithmic ones, and then also the exponential logarithmic inverse one. And you should be able to solve and simplify lots of exponential logarithmic equations now.